So welcome to this session A3 on non-well separation, and we will quickly recall what it means to have a correct by construction synthesis. In our GR1 synthesis, we always have assumptions and guarantees, and the semantics of such a specification is that as long as all the assumptions are satisfied, the system will guarantee that it satisfies all of the guarantees. So this is when we have a realizable specification, and the controller that we synthesize will be the one making sure that all of the guarantees are satisfied as long as all the assumptions are satisfied, right? It can always happen that an assumption is not satisfied. So for example, if an assumption was incorrect or the environment misbehaves, and then usually there's no way to satisfy the guarantees. Now, in the non-well separation is a very, very special case. A non-well separated environment can be forced to violate at least one assumption from some reachable state. So we are talking about the assumptions of a specification because they describe the environment. And we're saying that it can be forced to violate some assumption. So this is a very special case where an assumption is not violated because the environment chooses to violate it, but because it has no choice other than violating that assumption. And we will look at some examples because this is usually an inherent problem in an environment specification. So the environment is specified in such a way that it enables, for example, the system to force the environment to violate some assumption. And we will see that that sometimes is the only way out to synthesize a controller that satisfies the GR1 specification and is correct by construction, but very likely undesired. So here we have an example of a simple grid world. We saw this before. We have coordinates, we have cells from 0 to 5 and two-dimensional coordinates here, so two-dimensional grid. We have two positions in the corners of the grid, so 0, 0 top left corner and 5, 5 bottom right corner. Then we have some assumptions of how the commands that the robot decides to do are implemented by the environment. So the environment controls the position of the robot based on what system moves the system wants to do. We have these predicates of updating the position. So for example, if the system decides to move up, then this means that the coordinate, the y coordinate will be decreased by 1 and the x coordinate will stay the same. And these are the predicates implementing this. And then we have here two guarantees that need to be satisfied. So if the robot is at position 1, then it should ensure that in the next step it is in position 2. And we also always eventually want the robot to visit position 1, which then means that in the next step the robot has to visit position P2. So if we look at this, this looks a bit strange because this next step is the immediately next step. And there is no way that a robot that can only move one step at a time could travel within a single step. So basically we can only travel one coordinate at a time. We cannot move from 0, 0 to 5, 5. That's impossible. So we would expect that this specification is not realizable. So let's have a look. We'll check the realizability and we see it is realizable. That is surprising. We could now check why or how it is realized. So let's just check that in our we have a deterministic static symbolic controller. So now we're simply going to analyze the controller and see how is it going to win, or how is it going to ensure that from P1 it travels to P2. We will use the controller walker again. we will walk as the system player because that's the only one that we're interested in. We see the robot starts in position 2, 5, some random position, and the strategy is to go up. Okay, so we are expecting that maybe we are moving towards 0, 0. So yeah, moving up, then moving down. Moving down again, that's a bit strange. We would assume that we should walk to position 1, which is 0, 0. But yeah, what happened is the robot tries to move down, 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 and then eventually has a deadlock, forces a deadlock in the environment. So there is a problem with the environment. This controller definitely does not satisfy the guarantees, but we know that synthesis is correct by construction, so this controller does satisfy the specification. So the only way to satisfy the specification, if we don't satisfy the guarantees, is by forcing a violation of the assumptions. Now, we can run an analysis here. Spec_try_ons comes with a well separation analysis. We can say first diagnose well separation of the environment. So that's what we should do. And it says, well, the environment specification is non-well separated. So there is a problem, and the system can force the environment to violate some safety assumption from all initial states. So it's a very serious problem. Some of these assumptions here are leading to a problem. So let's try to analyze which ones. And the well separation menu also allows us to compute a non-well separation core. And this highlights a single assumption that is already enough to force assumption violations. So if we look at this single assumption that if we move up, then the y coordinate gets decreased and the x coordinate stays the same. So while x coordinate stays the same, there's probably not much that could go wrong here. Now let's see decreasing the y coordinate. Well, in the strategy that we saw, it was actually increasing one of the coordinates, but yeah, never mind. So one other way is also there are many possible ways, and one way is to decrease the y coordinate, and then once we are at 0, there's no way to further decrease the coordinate, but this is an assumption that says, well, you have to decrease it. We can't decrease it below 0 because that's the range of the data type. So here is an assumption violation. We had a fix here where we basically said, well, decrease the coordinate unless you are at 0 and then just stay the same. Yeah, this is how we find these kind of issues. And there is another example here. Now let's see if this one is realizable. It is realizable. So realizability and non-well separation do not necessarily have to come together. But what happens is that, as in this case here, there was no way that the guarantees could be satisfied. So the non-well separation actually allowed us to still realize the specification in a bad way, and that's why we want to debug this and maybe fix this. And here the repaired version is a fix. So now this one is probably no longer realizable. Yep, it's unrealizable because we can't just fly from P1 to P2 in one step. Okay, so in this case here, this specification is also realizable. Now let's have a look whether it is well separated again. If we diagnose it, it says it is non-well separated, and now this one is not from all initial states, but from some initial states or from some reachable states. So let's try to analyze what's wrong with this specification. Compute a non-well separated core. So now we are a little bit out of luck. The non-well separated core turns out to be the complete environment specification, so that's not narrowing it down, but it means that we need the interplay of actually all of these assumptions to force an assumption violation. So then let's have a look. We can also compute a non-well separation strategy, and the non-well separation strategy actually shows us how the system could force a violation. So what we see here is that the system forces the violation. It can only force the violation once car A and car B are true. So it cannot always force the violation. But once we have two cars waiting, the system could decide never to have a green light again. And then this assumption here that always eventually there will be not two cars waiting, this assumption would then be violated. These assumptions here, they say that the car waits until it gets a green light. So if we have a car waiting in lane A, we don't have a green light in A, then the car will still wait. So either we have to violate one of these assumptions, that the car magically disappears or runs the red light, or we cannot, the environment can no longer satisfy this assumption that there are no two cars waiting once we had cars waiting. So, and there are different ways to fix this. Actually, we could change again the assumption, and we say, well, you have to ensure that not two cars are waiting at the same time, or just when there are red lights, that's also fine. When there are only red lights, that's also fine. So here we are fixing the non-well separation by weakening an assumption. So that's one way. And now let's analyze this one. So this is now well separated. That's fine. That's the way we want it to be, because then there's no way to exploit this non-well separation. So usually the synthesizer will not try to exploit the non-well separation, but as we saw in this example, there's no way to realize the specification in the first place by satisfying the guarantees. So then it will have to exploit the non-well separation. So now this was one way of weakening the assumption, but there is another way where we can actually add an additional guarantee. This guarantee here could say that as soon as there is a car A, we will have a green light, and if there's a car B and not the car A, then we will have a green light for B. So basically there's a priority for green lights on road A, but if there's no car waiting at A, then we'll give a green light for B. And now let's see if this one is well separated. Yeah, this one is well separated, and the reason that it's well separated is because the well separation, we can take guarantees into account. So the very theoretic, strict version, we would only look at the environment, so only look at the assumptions. And in that case, adding a guarantee would not help us with the well separation. But in the default case, we usually consider to also assume that the system goes by its guarantees, and then adding a guarantee can actually make a specification well separated again. So with this guarantee, there is no longer any way that the system would be able to force the environment to violate an assumption. So now the task for this one would be to analyze the specification TrafficA3b and check it for non-well separation and identify the reasons for non-well separation if there are any.